The title of this presentation is How to Lie with Data, Statistics, Graphs, and Maps. The contents include an introduction to the book by Daryl Duff called How to Lie with Statistics, and then talking about how you use graphics to lie and the most common tricks to do that, and then a section on lying with maps. And as usual, I end my presentation with a concluding remark. The book of Daryl Duff, this is a version 2001. He's an American writer, best known as the author of How to Lie with Statistics in 1954. This means the book was published about 70 years ago, the best-selling statistics book of the second half of the 20th century. To your surprise, he's not a statistician. Huff was a journalist who wrote many how-to articles as a freelancer. The book is a fantastic primer on how we were tricked daily by the sneaky use of statistics. It's a must-read for anyone to more intelligently interpret news, media, and even medical research. Once you learn to see these tricks, you cannot unsee them. The book is text in most parts, very little tables and numbers, and a lot of cartoons like this one. Therefore, we should also recognize Mr. Irving Geis, who did the illustration. To summarize the book, I devised this method of mentioning very few takeaways from each chapter. The book has 10 chapters. Chapter 1 is a sample with the built-in bias, and I quote, "A purely random sample is difficult and expensive to obtain." Chapter 2 is called the well-chosen average, and it says when you are told that something is an average, you still don't know very much about it unless you can find out which of the common kinds of average it is. We have 3 types: mean, median, and mode, and I'm going to define them later on. Chapter 3, the little figures that are not there. Only when there is a substantial number of trials involved is the law of averages a useful description or prediction. Chapter 4, much ado about practically nothing. Sometimes the big ado or activity is made about a difference that is mathematically real and demonstrable, but so tiny as to have no importance. As you can see, the articulation of these takeaways is a lot of on the philosophy side of the statistics. Chapter 5, the gee-whiz graph. After truncating the line graph, change proportion between the ordinate and abscissa. This exaggerates a rise or fall. Chapter 6, the one-dimensional picture, and it says a pictograph, which depicts the frequency of data in the form of pictures or symbols, where the height width of each image is drawn in proportion to the data being reported, can be deceiving because even though a side is in proportion, the area occupied by the image can be a lot bigger. Chapter 7, called the semi-attached figure, and there are often many ways of expressing any figure. You can, for instance, express exactly the same fact by calling it a 1% return on sales, a 15% return on investment, a $10 million profit, an increase in profits of 40% compared to the 1935 to 1939 average. Chapter 8, post hoc rides again. And I like this example. It says there are two clocks which keep perfect time. When the first clock points to the hour, the second clock strikes. The important question is, did the first clock cause the second to strike? The post hoc fallacy we are talking about, if A follows A, then A caused B. Chapter 9, and in this chapter I mentioned two takeaways. How to statisticulate, I think this verb is invented by the author. Any percentage figure based on a small number of cases is likely to be misleading. It's more informative to give the figure itself. If your profits should climb from 3% on investment one year to 6% in the next, you can make it sound like modest by calling it a rise of 3 percentage points. With equal validity, you can describe it as a 100% increase. The last chapter asks 5 questions. The title of the chapter said 10, how to talk back to a statistic. You have to ask these questions. Who says so? How do they know? What is missing? Did somebody change the subject? Does it make sense? And we will give here in the coming slide some examples. For missing data, an example is not all respondents who should have completed the survey have completed the survey. This can be detected by looking at the total sample size for the survey. If you were expecting a survey of 1,000 respondents, but the sample is 575, then 425 are missing. Another example is biased samples. A report based on sampling must use a representative sample, which is one from which every source of bias has to be removed. If a psychiatrist say that practically everyone is neurotic, do you suppose that their impression has been biased by their line of work? Example of biased data. Asking a group of 9th grade graders what they believe the speed limit should be on a highway is an example of a sample bias. Biased average. There are 3 kinds of average, as we mentioned before: the mean, the mode, and the median. And these can be very different numbers, and reporters and others will pick the one that best support their argument. And these are the definitions. Explanations. The numbers 10, 10, 20, 40, and 70. The mean, called informally the average, is found by adding all the numbers together and dividing by a number of items in the set, which brings up 30. The mode, if a set of numbers contain the following digits 1, 1, 3, 5, 6, 6, 7, 7, 7, and 8, the mode would be 7, as it appears the most out of the numbers in the set. The median, if the numbers 7, 6, 9, 2, and 1, the median would be 6, as the numbers would be placed in order, and 6 is the number in the middle. Therefore, these 3 examples differentiates between the mean, the mode, and the median. The second section of the presentation is graphics that lie. And I like this quote: we tend to believe that what numbers say, but just because they are on a chart, that doesn't make them true. How? We are going to see now. Numbers themselves don't lie, but how we present them can be really misleading. there are good news and bad news. The good news are that there are some tips you can use to reveal the truth. But the bad news, a chart flashes by quickly on a TV screen and doesn't give you an opportunity to apply the good news. The most common tricks start by broken scales, show drama where it doesn't exist. Something that changes by 0.1% over 10 years and something that changes by 1000% in 1 year can look exactly on the same depending on the scale or range of values used on the chart. And this is an example. You have US GDP and another US GDP. The difference is the limits of the scale of the y-axis. To begin at 5.25% depicts a more dramatic scenario than reality. If you start at 0, you get a more realistic presentation of the change of US gross domestic product. Comparing two elements, it gets worse. When we compare two different elements, in this case, we are not just adding drama to the change, we are making unfair comparisons like this example here. We have percentage of victories and percentage of victories, and again we are changing the lower limit of the y-axis. When we don't show the full extent of the bars, the difference between bars looks much bigger than it really is, missing the point of the visual comparison. The second example is showing data on two different scales. Can make for an apples to oranges comparison, like this example here. We are comparing two things, US unemployment rate and US GDP change. Looking at the chart on the left could make you think US gross domestic product GDP surpassed the unemployment rate around March 2015, but that comparison is meaningless because again we are comparing oranges and apples. The third example is showing a correlation can imply causation. Two people doing the same dance moves may not be dancing to the same song. I like this quote. The same way, just because two sets of numbers follow a similar path doesn't mean there is a correlation, like this example here. We are comparing US unemployment rate with Hillary Clinton approval rate. The lines show a similar trend, but the relationship between Clinton's approval rate and unemployment seems improbable. The fourth example, ignoring population size makes rates impossible to compare. Still, when we are talking about where people live, it's important to have in mind how many people live there, and there is plenty of examples showing this. One of them is this. In the chart to the left, most dangerous cities are compared depending on total murders in 2014. The right, the most dangerous cities are compared based on murder rate in major US cities in 2014 per 100,000 people. Chicago and New York suffered more murders in 2014 than Detroit. But that doesn't mean they are more dangerous. If you look at how many people live in each city, the comparison changes greatly. As you can see in the left, we have Chicago and New York as first and second in rank, and if we compare depending on the population, Detroit comes number 1, followed by New Orleans. The fifth example is decoration can be deceiving. If you are making a chart to visualize amounts and you distort the way amounts are visualized, what's the point of making a chart? Therefore, be careful with decoration, and this pie chart is a good example. In the chart on the left, the percentage of Christians is the biggest value, but the larger number of green shows for Muslims because of the 3D effect. The concluding remark for this section is, of course, there are many more ways to lie with charts. Some subtle, some not, just as there are ways to mislead with words and pictures. The biggest enemies of chart cheats are context analysis and common sense. Try to apply those next time you see some shocking truths in the form of a chart. Lying with maps, which is the last section before the conclusion. It's an article written by Mark Monmonier. Darrell Huffs, the author of How to Lie with Statistics, was the inspiration for How to Lie with Maps, in which the author showed that geometric distortion and geometric generalization of data are unavoidable elements of cartographic representation. New examples of how ill-conceived or deliberately contrived statistical maps can greatly distort geographic reality demonstrate that lying with maps is a special case of lying with statistics. Most maps are massive reductions of the reality they represent, and clarity demands that much of that reality be suppressed. Issues addressed here include the effects of map scale on geometry and feature selection. Bar scales should never appear on map of the world, a continent, or a large country. Why? Because coastlines and other features are transferred from a spherical Earth to a flat map. These two maps here, the lower shows the corresponding portion of 1 to 250,000 map enlarged to 1 to 24,000 to reveal the impact of noticeably wider symbolic. Even though both experts cover the same area, but the upper panel is a same size black and white excerpt from the larger scale 1 to 24,000 map. Here is a map of the United States, and we concentrate on Maine and Massachusetts because of the way they are presented in this map. A geometric distortion is especially useful in portraying statistical data. For the United States is the visibility-based map, which replaces the contorted outlines of Maine and Massachusetts with simplified 5 and 13 point polygons, as I put them in red circles, instantly recognizable because of their relative location and characteristic shape. Here, the map shows crude birth rate in year 2000 by state based on equal intervals, cut points, and plotted on a visibility-based map. Have a look at the distribution of the different shaded colors. Here, cut points and frivolous fills. The usual result is 5 categories based on either equal intervals or a quantile classing, meaning that the previous map could be presented again with different categories. Like, as you can see, the one we saw before is to the left side based on equal intervals. But if we change the intervals using quantile cut points, we get a different map with different coloring. The same thing when we we look at these two figures. The statistical data like the special series of birth rates in figures 2 and 3 are easily distorted when map makers succumb to a software vendor's sense of what works without probing the data to discover what's meaningful. One must also make adjustments to avoid placing identical values in different categories. If you like to have a closer look of how the data looks like, we look at figure 4 here, where the number line describes variation in the data for figures 2 and 3. This simple graphic quickly reveals pitfalls like the possible assignment of Arizona and Texas, which have very close numbers, 17.5 and 17.8 respectively, to separate categories. Figure 5 here, the ability to explore data interactively can be an invitation to buttress serious arguments with biased map. For example, a polemicist out to demonstrate that American fertility is dangerously low might deceive a map like figure 5, might devise a map like figure 5 which assigns nearly 3/4 of the states to the lowest category. The opposite is here. A demagogue arguing that birth rates are too high would no doubt prefer this figure, figure 6, which paints much of the country as ominous black. Extreme views like these are useful reminders that maps are really manipulated. Because the classification here has the same weights, it doesn't tell you the bin range for each category here. Therefore, I prepared this map comparing figures 2 to 6, showing how the 5 categorizations are devised. For equal, the 5 are equal. For quantile, they are different. And for the low fertility map, they increase the low fertility bin, and for high fertility, they increase the high fertility to show their point of view that is different from the real thing. A map focusing on the number of births. Here we change how we look at the birth rates. Instead of relating them correctly to 100,000 population, here we use the number of births. Therefore, if the map focuses on number of births rather than the rate, has little meaning outside an education and marketing campaign pitched at obstetricians, new mothers, or toy manufacturers. Therefore, as we discussed at the beginning, it is better to use the population size to see the real message sent. Several remedies to the previous problems encountered in the previous maps is to use this kind of chart. This bigger means more metaphor of this dot array map affords a more appropriate treatment of the count data in figure 7, where one dot represents 10,000 births. Maps and bivariate correlation. Pairs of choropleth maps can purposely heighten or suppress perceptions of bivariate association, as we can see here. Here, this is the upper part of a map, and this is the lower part. In the upper part, we show the rate of population change percentage from 1960 to 1970 using 5 bins as before, where these are the bin ranges. But if we compare this the two lower maps are different representations of the same data, and optimization algorithms found cut points intended to yield displays that look very similar the lower left and very dissimilar to the lower right to the map at the top. Cut points for the upper map include 0, which separates gains from losses, and 13.3, the national rate. Therefore, the optimization algorithms showed us how we can display the same data differently depending about the intended message from the display. My concluding comment, as Darrell Huff eloquently demonstrated 70 years ago, consumers of statistical analysis and data graphics must be informed skeptics. This plea is usually relevant to map users who need to appreciate the perils and limitations of cartographic implication, as well its power and utility. Because abstract representations of data can distort almost as readily as they can reveal, analytical tools are also rhetorical instruments fully capable of lying in the hands of a malevolent, naive, or sloppily expedient authors. Huff's engaging little book performed a vital public service by calling attention to the power of analytical tools for self-deception as well as mass trickery.